Okay, so we're going to finish off integration by substitution, get a little bit more practice with it. I think the main way in which the problems here are going to differ from what we did not a moment ago, but from what we did in part one, is you're going to have limits. So they're going to be definite integrals, and there's something you have to watch out for when you're using integration by substitution and you've got limits, which can cause a common mistake if you forget about it. But we'll take a look at that in a moment. Just to get us into the swing of things, I'd like you to just have another go at using a bit of reverse chain rule. So it's not integration by substitution, but it's a nice reverse chain rule problem, but it's a kind of a hidden reverse chain rule problem. At least it's not necessarily quite that obvious what you need to do. So I'd like you to give it a go. It's a little bit of a test of your intuition and your ability to problem solve. Try out a few things, maybe do it wrong a couple of times and then get the right answer. If you want to try it without absolutely any hint at all, feel free to go ahead. Otherwise, I will give a hint in a moment, and then following that I'll give the actual answer. So if you don't want a hint, pause the video now. Okay, and if you're still here and do want the hint, then I'll give it to you. If you don't want it, just skip past. Here's my hint. The derivative of sine squared x is 2 sine x times the derivative of sine x, which is cos x, and that is equal to sine 2x. Okay, that's my hint. So with that, if you haven't already, see if you can finish it off. Pause the video now. And now let's look at the actual answer. So having potentially noticed this, well, how would you notice this in the first place is a point as well, I suppose. This does look like a function to a power multiplied by a derivative, except for the multiplied by a derivative part. The derivative of sine is definitely not sine 2x. However, if you had been tempted, sometimes this will make sense, sometimes it won't. If you'd been tempted to change sine 2x into this, oops, 2 sine 2x, then you might have seen, oh, sine squared does in fact go to 2 sine 2x. There is actually not an alternative way to do this integral, which would be to have written it this way, and then to just call this 2 cos x sine to the 9x. And you could use reverse chain rule that way. I think that might be the more obvious way actually, but I thought I'd just show you this little trick as well, because if you've got this in your mind, then you might be able to do it another way. So the way we're going to do it then is to try our initial guess, but to first rewrite this so that we've got a function to a power multiplied by its derivative. So I'm going to change this to sine squared to the 4. Right, so that's same as sine to the 8. So then if I do my guess, which involves raising the power by 1, then I get 5 sine squared to the 4 multiplied by the derivative of sine squared x, which is sine 2x. And there I've effectively got the answer, except I need to divide by 5. So it's going to be 1/5 here. That 5 goes away. Remember that this sine squared to the 4 is the same as sine to the 8x, so therefore this is my original integral. And therefore we have the answer. It's 1/5 sine squared to the 5, or in other words, sine to the 10x. You didn't have to necessarily do it that way. As I said, you could have also potentially done it by integrating 2 cos x sine to the 9, which is also equivalent to what we've been given. But I just thought this was a fun little shortcut if you happen to know the derivative of sine squared. Right, so let's continue with integration by substitution. Okay, so we're getting on now to doing the reverse of something we already knew how to do, which is we know how to find the derivatives of inverse trig functions, arcsine, arccos, arctan. We should know how to find their derivatives. However, now the question is, how do we do the reverse? Now, you might make the case that if I wanted to prove this, all I have to do is find the derivative of the right-hand side and show that it's equal to the left. Technically, that would prove the integral, because you're relying on the fundamental theorem of calculus that integration and differentiation are inverse operations in some sense. However, you might not always be given this bit. All right, you might just be asked to integrate this. And what do you do if you can't remember off by heart the derivatives, which you may not necessarily be expected to do? So what you want to do is use an integration by substitution. Now what I'm going to do is I'm going to give you the substitution you should use. We'll use it, and then I'll explain a bit about how we would know how to use which substitution to use. So let's use the substitution x equals sine of u, and let's see what happens. So I'll have 1 over the square root of 1 minus x squared dx, and let's find the derivative of this so that we can do our change of variables. Dx over du equals cos u. Okay, so let's just have that handy, and then the 1 minus x squared is going to become 1 minus sine squared u. And what is 1 minus sine squared? It's cos squared u dx. Square root of cos squared is just 1 over cos. We've got 1 over cos u dx. And now let's do our change of variables. Remember, dx is effectively equal to cos u du. Therefore, we've got here integral of 1 over cos u times cos u du. So it becomes the integral of, and everything's cancelled nicely, 1 du. The integral of 1 with respect to a variable is the variable itself. So our answer is u. But what is u? Well, u was arcsine of x, right? If you just take the inverse of both sides. So that's it. We've got the answer. Technically, this is u plus c. So our final answer would in fact be arcsine of x plus c as required. So how did we know to use sine u? It's a little bit of intuition, and it's a little bit of having seen similar problems enough times. So it'll come with practice. When you see, I'll throw up a few examples just to sort of get you a little bit trained on these things. When you see stuff that looks like this, I'm being a little bit vague here, but these kinds of things, I'm kind of making them up a little bit, but these kinds of fractions where you kind of got a 1 and then you're adding or taking away an x squared, sometimes it's square rooted, sometimes instead of a 1 it'll be a constant, sometimes instead of 1 plus x squared it could be like 3 or 9 plus 3 squared. You might have constants in there somewhere. But these kinds of forms, these are the ones for which you could use a trig substitution. Okay, and the way to know which one to use is to kind of, it is a little bit of guesswork, but it's also the case of knowing your trig identities. So the fact is, your substitution is supposed to make this thing look simpler. So if you thought to yourself, well, what trig identity makes that simpler? It's the square root of something, and that something is 1 minus x squared. If I tried cos, well, what would that give me? I'd get 1 minus cos squared is sine squared, square root that, I get sine. That works out quite nicely actually. The problem with that though is that the derivative of is that a problem actually? Let me think for a moment. Now in this case I think it would work as well. You'd get an alternative form which is equivalent. So maybe sine or cos could work. Okay, but for instance tan would not work because 1 minus tan squared isn't going to give you something useful in this case. However, you could imagine if it was say 1 plus x squared, because you know that tan squared plus 1 equals sec squared, and that tan and sec have a relationship in terms of they can kind of differentiate to each other. Tan differentiates to sec squared. Therefore, you could see that maybe something like 1 over 1 plus x squared might use a tan as a substitution. So I guess my attempt at telling you which substitution to use is summarized as being, look at the form it's in and think about what trig identities look like that. So which trig identities have a 1 taking away something squared, right? Or can be rearranged to look that way. But really, it'll be a case of just trying a few different questions and getting used to which trig identities to use. Okay, and then the other thing I want to talk about when we're doing substitution is changing limits. So if you've got an integral, and let's just make one up for a moment. Let's say from 0 to 1 x squared dx. Okay, in fact I won't choose 0 and 1 because 0 sometimes causes problems. Let's say 1 and 2. I just want to remind you first that within this notation there's kind of something that I want you to think about in terms of the limits, which is these are kind of like invisible x's here. So really, if you wanted to make it very clear, this is really what you're doing, right? You're saying the integral of x squared dx, where x ranges from 1 to 2. But because we have this thing at the end of the integral, and it's clearly an x here, then these x equals are kind of redundant, so we don't put them in. So the standard notation is to just put numbers, and it's assumed you mean from x equals 1 to 2. However, that starts being a problem if you're going to mix variables by using substitution. So what we'll see, I think we'll do it by example, what you'll see is that when you change the variable, you change the dx to du for instance, you also need to change these x's here to u's. And ultimately what that means is the numbers here are going to change. So your limits will change along with the expression. If you forget to change your limits, then your integral will no longer have the correct answer, which should make sense, right? You can't just change the numbers and get the same answer. It's only an issue for definite integrals. For indefinite integrals, it's not a problem because there were no limits there in the first place. So let's take a look at an example of doing this. Or two examples. So first off, integral from 0 to 2 of x times x plus 1 cubed. Now we're not given the substitution, but hopefully with a bit of intuition you can start to think, okay, the thing that's awkward here is the x plus 1. So let's substitute that with something easier like u. Let's then also immediately find the derivative, which in this case is just 1, which effectively means this change of variables should be very easy because du is going to be the same as dx, right? I forgot to put dx here. So then let's rewrite this as the integral from 0 to 2, and I'm going to change these x's first. So this x plus 1 is just u and then cubed, and then this x here is actually u minus 1, right? By rearranging this thing, x is u minus 1. I'm going to keep this as dx for a moment. So as soon as this dx gets changed to a du, at that exact moment, you need to also change these numbers, right? So remember, secretly, this 2 is x equals 2, and this 0 is x equals 0. So let's do the change now. So the expression is still in terms of u. Dx is apparently just the same as du, so we can easily change it, but now we need to change the limits. When x equals 0, what is u equal to? When x equals 0, u equals 1. And when x equals 2, what is u equal to? Looking again back at our original substitution, it's equal to 3. So that means these two limits, 0 and 2, need to be changed into 1 and 3. So I change it here. And now it's the same, right? So this ultimately is just a number, right? It'll evaluate to a number, and it's going to be exactly the same number as whatever this evaluates to, which means we can now find the integral and evaluate it. So it's the integral from 1 to 3 of u to the 4 minus u cubed du, and from that point it should be fairly self-explanatory what to do. Fifth u to the 5 minus quarter u to the 4, put in 3, put in 1, find the difference. Should come out to 28.4. Okay, this is just standard, isn't it? So the tricky part is getting it into that form so that you can integrate it. Cool. All right. Let's try the other one. I'll just fast forward. So now we've got the integral from 0 to pi over 2 of cos x times root of 1 plus sine x. In this case, that root, or the power half, is the awkward bit. So let's use a substitution on that. Let's say u equals 1 plus sine x. And let's differentiate the substitution so we can figure out the change of variables. So in this case, this comes out quite nicely actually. Cos x times dx equals du. So I'm going to make use of that actually, because if we rewrite this so the cos x is on the left hand side, then we get this, and we can see quite nicely then this thing is just going to end up being du. But I won't write du yet because I haven't changed my limits. So that 1 plus sine x is just u, so the half, and cos x is du, and now we're going to have to change those variables. So we need to change it from 0 and 2 pi. So remember, those were secretly x equals 0 and x equals, did I say 2 pi? Pi over 2. So let's see what 1 plus sine x gives us. 1 plus sine of 0 is just 1. And 1 plus sine of pi over 2, what's sine of pi over 2? It's just 1. So we get 2. So now we can put that in our limit here, which is get 1 and 2. And that's exceedingly simple. We now just have 2/3 u to the 3 over 2, evaluated from 1 to 2. So that's 2/3 2 to the power of 3 over 2 minus 2/3. And we can then even write this as follows. Let's make it look a bit less confusing. 2 to the 3 over 2 is just square root of 2 cubed. Well, in this case 2 root 2. So in which case we can make this even nicer. So let's not just take out 2/3, let's take out, oh no, actually, sorry, we can't make it as nice as I thought we could. No, we'll just have to stick with that. 2/3, 2√2 minus 1. Because that 2 to the 3/2 is just √2 cubed, which is 2√2. Cool, and that's our answer. So again, the substitution is the main bit of working, and just be really aware of this process that you have to do with the limits. Usually a question will be kind and the limits will make sense. I guess I'll just give you another tip. This isn't so much a real world tip, but an exam style tip, which is if the limits are angles like pi/2, then your substitution is probably going to involve trig functions. It's not necessarily always the case, but it's a good hint there that it will. In any case, the integral itself had a lot of trig functions in it, so that should also set off your alarm bells that you want to use a trig function substitution. Cool. Cool, so practice questions all fit in one slide, mainly because they might take a bit of time to attempt. That last one is a little bit tricky if you haven't seen it been done before. So I want to give you time to try them. Have a go at these, try and finish them all, it's just the one slide. I did mention, so this is, these sort of weird forms I was talking about. You've got roots of 1 plus x, or you've got roots of x squared plus 4. My hint for those two is you're probably going to be looking at trig functions. 7 is very similar to one of the examples we did. In fact, is it a bit too similar? How exactly does it differ? I don't think it does too much. So I guess that one's more going to be a test of your ability to do it without looking back at your answer. What I suggest for 7 is also try the sign substitution. Try doing it both u equals sine x and u equals cos x, and see where you end up. Do you end up getting the same answer, or does one of them lead to a dead end? That'd be interesting to know. Yeah, and then 9, your training wheels are off, and you've got to find the substitution yourself. Cool. All right. So see how you do on those. Let me know if you need any help. You can pause the video now.